Yes. Seems like it's recording.
Okay. Well. All right. So do you have any questions, comments? No? Okay, so I think we can continue then this exercise sheet 2. Where it is. Yes, so we were dealing with this exercise 3, I believe. And what remained was exercise 2, I think. And yes, this exercise 7, probably. Okay. So let's do exercise 2. I don't know, I give you 5 minutes if you wanted to think about it. So the goal is to write, to somehow transform these sentences using quantifiers and some mathematical expression. Okay, so try to do it.
Did we not talk of all the cases of exercise 3?
Sorry, say it again.
We didn't talk about all the cases in, well, all the different combinations in exercise 3. I mean, maybe we did it quickly, but I thought we had. I can't remember.
I think we did all the cases, but maybe...
Yeah, we did too.
Yeah?
Yeah.
Okay, then Sarah, if you have any question on one of those, maybe we went a bit fast on number 4, I believe. Yeah.
No, I had asked my question about number 4 and you had answered.
Okay, okay.
Hello.
Yes.
I'm apologizing for being late. I have a problem with my internet, so I had to join in with my phone's internet.
Okay, no problem. We're dealing with exercise 2. I just gave everybody some time to think about it. And yes, we're going to correct it soon.
Okay, thanks.
Welcome. All right, so the first sentence to be translated is the function f from R to R is bounded from above. Okay, so we have all through this exercise, we have f a map from R to R. And the first one is f bounded from above. Okay, so who would like to try? So Eva? Yes, Eva. Eva is not answering, or she cannot hear us.
So sorry, I didn't have my mic on. Can you hear me?
Yes, yeah, perfect.
Okay, so there exists M belonging to R, such that for all X belonging to R, F to X is smaller than M.
Yes, perfect. So the thing is for this sort of statement. So basically, F is bounded. So here it's bounded from above, but it could be, well, there's a notion that it is bounded in some way. But what is important is you say it's bounded, but yeah, it means it's bounded by something. There is a bound. So you need to define this bound. So there exists some value here. Eva named it M, such that for any x, f of x is smaller than m. So it's really bounded from above. You see, there's no absolute value or anything. It's just it is the value is always smaller than this capital M. Okay, so the goal of the exercise is just to see that as soon as you say, for instance, it's bounded in some sense or another, it means there is a bound in the story, so you need to define it. So there exists some M, which is valid for any X, okay? So the situation we have here is really something like that. So you have this capital M here, and your map F is bounded from above, so it's always smaller than this, this capital M. You see that here I draw the picture so that it can go, it is not bound, it doesn't need to be bounded, so it can go pretty low, but it is bounded from above. Okay, is it clear for everybody? Yeah, okay. So the next one, sorry. The next one is the function f is not bounded from above. Nathan, can you please tell us?
So for all x belonging to R, there exists one y belonging to R, so that f of y is bigger than f of x.
Say it again, please, Nathan. I was
For
writing
all
at this.
x belonging to R, there exists one y belonging to R, so that f of y is bigger than f of x.
Okay, so f of y is bigger than f of x. Okay, yeah, that's a way of saying it. It's true. Let me think. Is it really? No, I don't think it's true. I don't think it's true because you could have some sort of asymptote. Okay, so imagine a function like this, and here it has some sort of asymptote here. So it's getting closer and closer, but never touching it. So I'm not able to draw this, but and it means that for any x, you'll be able to find, so for any x here, you'll be able to find a y such that f of y will be larger, but still it is bounded by this capital M.
Okay.
You see what I mean? So,
Yes.
So yeah, it's not exactly, it's not strictly speaking not bounded from above, but yeah. Okay, so let's try it. How can we have it differently then? What is this sentence compared to the first one? So,
Oh, sorry.
Not the first one.
yes, I don't know who is speaking, but it's not the first one indeed. So if you just take the not in the expression which was above, so if you take the not in here, what do you have? So Etienne.
So you get from, for any M belonging to R, there exists one X belonging to R, for that f of X is bigger than M.
Yeah. So which makes sense if you think about it, because basically what you're saying that if you want to say it's not bounded from above, it means that whenever the M you take, you can always find at least one X, which of course I'm going to write this way. It depends on M, such that your f of X, okay, so that's a bad example, of course. I should be more precise in my drawing. So you see for this X, the f of X is larger than capital M. But if M gets larger again, okay, so if M was bigger, then you need to find you need to find an X of M So this is x of this green m. You need to go further in order to be able to get above m. Is it clear what I'm saying?
Yeah, just a question. I tried thinking about it, and I found a solution. There does not exist an m which belongs to R, so that for every x, f of x is smaller or equal than m.
Okay, so let me write it down. Say it again. There does not exist m.
Which belongs to R,
Yeah.
so that for every x that belongs to R, f of x is smaller or equal than m.
Mm. Yes, somehow. Mm. Yes, so somehow this is really the negation. Yeah, because, okay, in a sense, the thing is, there does not exist a m such that, okay, it is really the negation of this, but it's what I mean. It's really like putting a knot in front. It's like putting a knot in front of everything here, but it doesn't tell much. In fact, it's not really. There does not exist a m. Well, this we don't know exactly what it means. It doesn't exist.
The way I thought it is just there
You know,
exist a limit for every x.
Yeah. The thing is, this is not really well defined in a sense.
Okay.
So yeah, I would not write this. I think it's better to really use this because this is really, you quantify. So you say for any m value, you can find an x such that blah blah. So
Okay,
I think
like
this is really some sort of translation in English of the knot of this, but it's not. It doesn't express anything. Okay.
Okay, thank you. I'll use the blue one then.
Yeah, I think it's more. It describes more what is going on, because here you see that the only option for not being bounded from above, it means morally that it's not like it's going to tend to plus infinity, but it means that there are always points, there are always x, basically, where the f of x is as large as I wish, in a sense. So meaning that any m I take, I know there will be an x of m such that f of x will get above this m. But it doesn't mean it converges to plus infinity.
Okay, it makes sense.
So just to make a drawing which is probably, I hope, more clear. So here we go in subtleties of functions, and we were going to see this already for sequences, for numerical sequences. But you see, a function like that, it's not bounded from above, but it is not converging to plus infinity neither. You see it, guys? I don't know, this is maybe a too technical discussion, but okay, so let's stick to the exercise. We were, so x sinus x, yes, something like that. Yeah, exactly. Some sort of oscillating function. You also have all, yeah, you can, every time you play with, basically with the frequency of some trigonometric function, you will end up with this sort of example. So what did we say? Function is bounded. Okay, I come back to the whiteboard. Well, okay, question 3, f is bounded. Okay. So somebody? Rémi, yes. Yes, Rémi. Maybe the mic is off. Rémi, we can't hear you.
Sorry, I forgot to turn my mic on.
No problem.
There exists A in R such that for all x in R, the absolute value of f of x is inferior or equal to A.
Okay, so I write it down and then we comment. For any x in R, the absolute value of f of x is
Greater or equal?
greater or equal.
No, inferior or equal, lesser
Oh.
than or equal, sorry.
Okay, okay. Okay, yeah, so I would say almost perfect. There's just one thing. Nathan, maybe you want to say something?
So maybe there are different bounds. So maybe, for example, it goes never over 10, but it goes under -10, for example. I
Well,
don't
then
know
it's
how to
not.
explain it, but maybe the bounds are not the same.
The bounds are, yeah. So let me explain this. So I'm going to. It's almost this. There's just a small thing I would like to change. So indeed, you could say this. So let's put this in parentheses just for a second. So if you think of a function which is bounded, I don't know, somebody else in the direction of what Nathan has said. Somebody had something else? Leo?
Yeah, the way I did it is I just made two bounds. There exists an
Okay.
L, there exists an M for that every R. F of x is smaller than L and F of x is bigger than M.
Okay, so that's exactly, this goes in the direction of, so there exists LM in R2. Ah, this is really shitty the way I write it down. Okay, let me, So let me explain this. So we can say there exists a lower bound, there exists an upper bound in R squared, such that for any x in R, I have f of x, which is between this lower bound and upper bound. So maybe it's more natural for everybody that we have this lower bound L, this upper bound capital M, and my map is somehow in between these two things. Okay. Now, the thing is, what Rémi suggested, this second formulation is equivalent to the first formulation that Rémi was suggesting. Basically, what is the difference between these two things is just that in the formulation of Rémi, basically Rémi chose, so say this value capital M is larger than this value L. So basically Rémi chose some value minus M here, and he chose A equal to M. And then this is true that this guy, this f of x, is larger than minus M, and it is smaller than M. Okay, it is true that you have f of x between minus M and M. So it is true that f of x in absolute value is smaller than M. If you do this, there's just one small thing to change in what Rémi wrote or said, It's just usually you take A in R plus. I mean, it is not wrong to say that A is in R, but you see that from this very formulation, oops, sorry. You see that from this very formulation, f of x is a positive number, a non-negative number, so A has to be a non-negative number. Okay. Nathan, you wanted to say something?
Yes, I wanted to point out the positive, so that A had to be positive.
Yes, exactly. So these two formulations are equivalent. It's just I prefer in the one of the form that the one of Rémi. Don't forget to put R plus here, because A by definition here has to be non-negative. Okay, it's not wrong if you write with R, but it's better to keep in mind is R plus. The second formulation, if it is more natural for you, you just keep the second formulation. Okay, but it really depends on how to use it. So if you just want to prove it is bounded, you can use the first formulation. You see the first formulation is less precise because this minus m, it's less precise than the original L bound that we had, okay? But if you just need a bound, this is enough. If you want to be very precise about your function and you want to be sharp, so-called sharp in bounding it, sorry, then you might use the two bounds, lower bounds, upper bounds. Is it clear? So myself, very often I'm going to use the first formulation, the Rémi's formulation with only one bound. Usually this is what I do. Yeah. Okay, guys, you're sleeping. Very few of you answer. Okay. So what's next? Can I erase this board? Yeah.
Yeah.
Okay. What's next? So bounded. Question 4. F is not bounded. Okay. So somebody else. Jonathan, yes, please.
OA element of R plus, there exists an X element of R such that the modulus of f of x is greater than A.
Perfect. Yeah, that's perfect. So basically it means, with words, whatever the largest value you think of, you will always find at least one x such that f of x is above this largest value. Okay. So this means, once again, it's not exactly like it tends to plus infinity, but this is the idea. It gets as large as one can think of. So I think first was Equine and her team. Noreen and Tiziana. Yeah.
Is it possible to say for any x in R, f of x belongs to minus infinity plus infinity?
No, because a function which is constant, the function constant equal to 1, for instance, it's bounded, but it satisfies what you say.
Oh yeah, okay.
The fact that you say it belongs to R, it doesn't mean that it has to take all the values in R, so to speak.
Okay, yeah, thank you.
Yeah. Also here it's really the negation of what was written before, and what was written before was there exists an A such that for any X, blah, blah. So you really take the negation piece by piece. Nathan?
I do not agree with this assertion because f can be bounded from above or from below as long as it's not bounded from above and for example, so this means it is bounded from above. It is not bounded from above or it is not bounded from below. But it doesn't mean it's not bounded from both sides.
No, it doesn't mean this. It doesn't mean this. And it doesn't mean this. This formulation doesn't mean that it's bounded from, okay. Okay, let's write what you say. So let's put it this way. So what is true is that f is bounded. It's equivalent to f bounded from above and f bounded from below. This is true. So if I want to, you see, so if f is not bounded, it means indeed that f is not bounded from above or it's not bounded from below. And you see that these two situations fits here.
Yes.
You see, let me take an example. So imagine I have a function which is bounded from above, but not from below. Okay, so my maps say, imagine you have an asymptote here, but then it's bounded from above. You see that anytime I take some a here you have the minus a, and you see that I'll be able to find some x such that f of x will be below minus a. So in absolute value, f of x will be larger than a.
Yes, I misunderstood the English phrase of is not bounded. I thought it couldn't be bounded from either side.
Okay. No, that's really the not of bounded. Okay, others, it's fine. Okay, so I erase this. And so it's not bounded. Okay, function does not vanish. Okay, does not vanish. Okay. So
actually, when I'm co-host, I can't raise my hand.
Okay.
Could I answer this question?
Yes, sure.
So for any x in R, f of x is different from 0.
Yep. Yep. What is f vanishes? Benjamin.
Yes, I didn't hear because you were cut from me, but I heard my name.
Mm-hmm. Yeah, I'm just I'm just asking. Can you? So thank you to Tristan to have translated f does not vanish. So this is true. So just what would be f vanishes? What is it equivalent to?
There exists an x belonging to R, and like f of x equals 0.
Yes, that's it. So no trick here, guys. Just f vanishes. It means it has some 0. So there exists some value such that this value is a 0 for f. So f of x equals to 0. F does not vanishes means it doesn't have a 0. Put it differently, for any candidate to be a 0, it is not a 0. So you see the way of thinking. It's a bit strange, but at least it's quite descriptive. Right? Okay. Okay, so I erase this. What is the last one? The last one was the function is not constant equal to 0. This is more interesting. So this is not the function constant equal to 0. So somebody else? Thank you, Remy. Noémie. Could you please tell us?
Yes, I wrote that for there exists at least one X in R. Actually, I wrote the same thing as 5, such that f of x is not equal to 0.
Yeah.
Okay.
So yeah, that's good. In fact, that's just something. It's the same thing as 5, because in order to see what's going on, what does it mean? F is the function. So I take this shortcut fct for function equal to 0. So constant equal to 0. This means that this is a function such that for any real value, f of x is equal to 0. Okay, so not being the constant function equal to 0, it means this. So it means there is at least one value where f is equal to 0. In other words, it means f vanishes at least once. It not vanishes. Sorry.
Yes. Okay.
not vanishes. Yes, there is a not constant equal to 0. Yeah. Okay. So, for instance, in this example, a function which is always equal to 0, but at some point is not equal to 0, this would be fine. It's a strange function, but it would be fine. It is not the function constant equal to 0. Okay. Good. So yes, that's it for this exercise. So you see, it's just translating. We will see when you will do with Jessica Martin, you will do some analysis of functions. You'll see that this expression, it's really fundamental to translate, for instance, what is the right notion of limit? What does it mean for a function or for a sequence to have a limit? We're going to see this together, ready for sequences. Using quantifiers to try to translate this notion is really fundamental. Okay, so I think we're almost done with this exercise sheet. We did all these exercises here, 1 to 5. Yes. So I think what remained was exercise 7 for sure, and maybe exercise 6.
That's right, just 6 and 7.
Okay. So did you have time to think about this? I did not say to prepare them, but maybe you have prepared them. So I give you some time to think about this. Let's start with exercise 6. So since we have not done exercises on Cartesian product, there will be no Cartesian product tomorrow, okay? Even if we do exercise 7 this morning, it's somehow too late. So, somebody wants to try exercise 6? Remy, good, but the other people who have not spoken much this morning. Noemi, you want to try? Okay. So, so we have A union B is equal to E, and we want to prove this is equivalent in the first place to A complementary, I think. It's included in B, something like that.
Yes.
Okay.
But first I said that not A included in B was equivalent to not B included in A by contrapositive. So we only had to prove like one thing.
Sorry, I'm just. You say so. A is equivalent to this by contrapositive. So this is true.
Yeah.
This is a contrapositive. Yes, so we have to prove exactly one thing. So these two last, equivalents, so the equivalence between this and that, it's done just by contrapositive. Yeah,
yes.
That's true. Okay. Is it clear for everybody? This? Yep. Okay. All right, so I listen to you now for the first equivalence.
Okay, so I first proved that A or B equal to E implies not A included in B.
Okay, so the first thing is to prove this.
Yes.
So, yes, perfect. So what do you do?
So I let A and B included in E square.
Mm-hmm.
I assume A or B is equal to E.
So I write it down this way.
Oh, yes, yes.
No, it's fine. A union B, E is equal to E. Okay, yes, sorry. And then?
And then we prove not A included in B.
Mm-hmm.
So A or B equal to E is equivalent. Wait.
Oui.
Okay, yes, A or B equal to E is equivalent to A or B included in E and E included in A or B.
Okay. That's true.
Which is equivalent to A in E or B in E and E in A or E and B in B. Okay, sorry.
Since I was lost. So, sorry, say it again.
Yes, A is included in E or B is included in E.
Mm-hmm.
And E is included in A or E is included in B.
No.
Oh no, it's not right.
No, that's not true. So E is included in A union B. It doesn't mean that A is included in A or E included in B. So this is not true. Let me give you an example. So you have some A here, you have some B there. So that's not what's going on in that case. And then we're saying some E guy is included in the union. So you can imagine something like that. You can imagine that the E set is, so E is a union of these two things, say E1, E2, and E is a union of E1 and E2. So you see, E itself is included in the union because any element of E belongs to the union, either to A or to B. But it is not true that E itself is included in A or E itself is included in B.
Yes, I get it now.
You see, there are some pieces. So one way, is it clear for everybody, this counterexample? But that's a sorry, Noemi, but that's a good mistake. I think this is the kind of things it's good to see these sort of problems. Okay, so I think one way of doing it is just to write down what it means, the inclusions that we want. So the inclusion we want is A bar is included in B. So in other words, I think there is another proof after that, guys, if you want, but then you can say, you can take the following thing. You started from the right place. So you can say, let X belonging in A bar. So X does not belong to A. Okay, this we know. So, okay, let X does not belong in A bar, so X does not belong to A, and X belong to E, because A bar is a complementary of A in E. So you see, it means, so X does not belong to A, and X belong to E, and E is A union B. So I have X does not belong in A, and X belong in A, or X belong in B. So by Morgan law, I can somehow expand, and you see that if I expand, I have X in does not belong in A and X belong in A, which is false, or X belong to B and it doesn't belong to A. You see, Noemi? And others?
Yes, it's much easier than.
Yeah, well, then it's, I mean, it was worth trying, but yeah, it's always difficult to, it was worth trying. So you have X in B and X does not belong to A, and yeah, so X belong to B. Okay, this was the conclusion. So this proves that A bar is included in B. So we proved basically this direction. For these kind of things, I know it's strange somehow. Let me think. No, I was mentioning another proof, but that's not easier. No, that's not easier. Okay, so we have one direction. Okay, thank you. Rémi, you want to do the converse implication?
The last thing I didn't do.
Ah, okay. Okay, so is it fine, everybody, if I erase this page so that I move to the next one, to the converse direction? Okay, so let's do this. I didn't want to erase the whole page to keep what is written on the top, but in fact it was way quicker to rewrite it down. Anyway, so yeah, so now let's move to the proof of this direction. So assume A bar is included in B. So in the first place, Noemi, you said let A be parts of E. In fact, we are not really obliged to recall this at this stage because here the statement, it involves some A and B. So it's already stated what are the objects A and B. But anyway, it doesn't cost much to recall it. It's not a problem. It's probably better to recall it more than less. Okay, so so I assume A bar is included in B, and we want to prove that the union is equal to E. So obviously, the union is included in E. Okay. Nathan, you wanted to say something?
Yes, I wanted to do the proof.
Okay, okay. Then I.
So the complementary of B included in A can let X belong to E.
Yep.
The complementary set of B included in A is equivalent to for any X in E. If X belongs to the complementary set of B, then X belongs to A. And then I undo I write X belongs to the complementary set of B as X belongs to E and X does not belong to B, implies X belongs to A. And then I transform the imply into the not or just so it's X does not belong to E, or X belongs to B, or X belongs to A, and I redo an implication but on another place. So X belongs to E implies that X belongs to A, or X belongs to B, and so X belongs to E implies.
Yeah, okay, so at the end, I think, okay, let's summarize, because you wrote it in a lot of steps, but at the end, I think you basically have a disjunction of cases.
Yes.
What I mean is, you see, everybody, so basically I take X in E, I want to prove it's in A union B. So there are two cases, because I'm going to make the distinction with A in that case. So Nathan will somehow use, I think, this assumption, B bar included in A. So, but this is the same. So basically I have two cases. So let me write it down so that it's easier. So we have two cases. The first one is X belongs to A. In that case, then X belongs to A union B. Okay, so I chose some X in E and I said, okay, eventually X belongs to A, then in that case, it's fine, it belongs to A union B, so I'm good here. The second case is X does not belong to A, right? But as A bar is included in B, this is our assumption, then X belongs to B, and so X belongs to A union B. So at the end of the day, in each case, I end up with X belong to A union B. So X belongs to A union B in both cases, okay? And so, oops, sorry. And so E is included in A union B, all right? So I think this is what you did, Nathan, but you used it in maybe a little bit more complicated way.
Yes.
Yeah. So, but this is the idea was right. So it's disjunction of cases. Sorry.
Could we have used the union instead of disjunction of cases? X is in E, implies X is in A union not A, implies X is in A union B.
That's true. That's true.
Okay.
Yeah. Well, that's correct. That's correct. Yeah. Everybody else, is it fine? Yeah. Okay. Yeah, and then as Noemi said, so the last part was just the contrapositive writing of these two expressions. Good. Okay, so we have finished this exercise. Now let's move to exercise 7. Okay, so we have E and F two sets. E1, E2 are subset of E, and F1, F2 are subset of F. And we have to prove that the Cartesian product of E1 with F1 intersected with E2 times F2. This is in fact the Cartesian product of the two intersections, so E1, E2 and F1, F2. And we have to prove almost the same thing for the union, but you see that for the union, we have only an inclusion, and that the converse inclusion is probably wrong. And it is proved that this converse inclusion is wrong. And you have a counterexample, which is given in question 3. Okay. Well, okay, guys, so this exercise we're going to do to finish next week. We're going to finish the lecture also next week. No, the lecture, I mean this chapter 4, I think we were studying, and we're going to start chapter 5. So we get a little bit away from this logic and study some special type of relations, it's called. And then we move to numerical sequences, okay? So this is the end of this fundamental backgrounds on reasoning, basically. Do you have questions for tomorrow? I mean, I don't want us to start this exercise like 5 minutes before the end of the class. Yes, Nathan.
Do we need special paper to write the test, or can we write on regular GNA4?
You can write on regular paper. So I think those of you who train for the homework, you trained in scanning basically the work. So this was perfect for me. For everybody, it was very clear, and I could write on your tests. So it was quite convenient for me. Thea, wanted to ask a question. Sarah, your mic is off.
Sorry, I keep forgetting. But I was wondering if, because there was one of the exercises in the lecture where there were sets with the polynôme de second degré.
Yep.
And I had quite a problem with that one, and I was wondering if there were going to be difficult sets. Well, I don't know that I found it difficult, but sets that are quite complicated like that, or if it's going. Okay.
I've planned an exercise where there is a square, but you have only to expand the square, so that's fine. Nothing to be solved.
Thank you.
Okay. Georgia, Queen, and her team.
So tomorrow morning, do we go on Zoom, or do we just go on Moodle?
Yeah. So the thing is, right now it's not there, but so yeah. I think it worked well for those of you who did this homework on Moodle. It worked well to access the page and to drop your test and everything. I think this was quite okay. So we're going to do exactly the same thing. So tomorrow I will send you an email probably this evening. So it will be on the Moodle page of Math Zero, but be careful, the Enginesa Moodle page of Math Zero, so the one in English. There will be a new section called CC1 or maybe Test 1. I don't know how I'm going to name this. And you will be able to access the file from, I think I will put it just before 8, so like 5 minutes to 8 for tomorrow morning. So you can access the file. I will look at my emails. I will probably also do a Zoom link in case some of you need to contact me, but I don't want you to contact me to question me about the test. I want you to contact me to question me about technical problems. So if you have a problem, then I can send you the test by email, for instance, or something like that. And so you have 1 hour and a half to do the test, and then I will wait that everybody has done the scanning and put it on Moodle. Okay.
Okay, thank you.
Somebody wanted to say something, Remy? Yep.
Can we go over the exercise 2 of the assignment, the last 2 questions, because I didn't get them right, and I don't know, I didn't understand them properly.
Of what? Of the
homework assignment.
Oh yeah. So I'm not sure I have the homework here on the iPad. I mean,
I can send it in Zoom if you want.
Yes, please. If you can share with Zoom, it's easier because yeah, it's not on the same folder on my iPad.
Okay, sent.
Maybe you can't.
I can't, but I sent it as a file in the chat. Maybe you can get it from there.
I don't see anything. Let me just Rémi. Okay.